So we are next starting the exercises. Exercises 1, 3, and this is the first one. Two functions are given, f and g. F maps the set consisting of 1, 3 and 4 into the set consisting of 1, 2 and 5, and g maps this set into this two element set consisting of 1 and 3. And the formulas for f and g are these. F maps 1 into 2, 3 into 5 and 4 into 1. That means 1 goes to 2, 3 goes to 5 and 4 goes to 1 under f. And g maps 1 into 3, 2 into 3 and 5 into 1. So 1 and 2 both go to 3 and 5 gets mapped onto 1 under g by g. So we have to write down the composite G composition F. We first figure out the domain and codomain of this composite map. The domain of this composition is of course the domain of F, and the codomain is the codomain of G. That means this G composition F maps 1, 3, 4 into 1, 3. So accordingly the inputs are these three numbers 1, 3 and 4. So let us first evaluate this function at 1. So if the input is 1, then of course by the definition of composition this is g of f of 1. Now what is f of 1? You look at the formula for f. F maps 1 onto 2. So f of 1 is equal to 2. So we get g of 2. And g maps 2 onto 3. So that's how we get 3. So G composition F maps 1 onto 3. So next we are going to look at what this function does to the other two inputs. So the next input is, you can actually take any one of the remaining two. There is no first, second and third in a set, but we take 3 next. So G composition F of 3 is G of F of 3. Now what is f of 3? F of 3 is 5. So that way we get g of 5, and g of 5 is 1. So this composite function maps 3 onto 1. And then next we see what it does to 4. G composition f of 4 is g of f of 4. F of 4 is 1. So you get g of 1. And g of 1 is 3. So that's how you get 3. You can either just simply end the solution here, or you can also decide to write G composition F as a set like this. So if you want, you can do that. That part I am leaving to you. So what set will it be? It will be a set of 3 ordered pairs. What will be the ordered pairs here? One of them will be 1, 3, another will be 5, 1 and another will be 4, 3. That's it. Next, number 2. Here we have 3 functions f, g and h, and all of them map r into r, the set of real numbers into itself. Then we have to prove these two identities. F plus g composition h should equal f composition h plus g composition h, and f dot g means the product of the two functions f and g. Composition h equals f composition h dot g composition h. So what is it that we have to prove here? That these two functions, the one on the left hand side and the one on the right hand side, are equal. They are the same function. So you need to show two things for this. The first is that both of them have the same domain and same codomain. That is one thing. And the second thing is that they behave in exactly the same way, in the sense that for a given input, they assign the same output. That means the values of both these functions at a given input should be the same output. And regarding this domain and codomain, it's a simple thing to notice that since all the functions involved are functions from R into R, and because of the way these operations have been defined, addition of two functions, and composition of functions, the left hand side as well as the right hand side are both functions from R into R. They both map R into itself. So that means we can at least now ask if they are equal as functions. So everything now will depend on whether they give us the same output for a given input. So we start our calculation, or rather argument, anything you can call it, by taking any input. Because the common domain is R, so it's any real number, let's call it x, and say we apply this function on x, we evaluate this at x. Because the outer operation is composition, it is first of all a composition of two functions. One of them is f plus g and the other one is h. So that is why the composition is this. When you evaluate it at x, it becomes this, f plus g of h of x. That means here you are looking at the value of f plus g at the input h of x. But then by the definition of class itself of two functions, this is f of h of x plus g of h of x. That is the meaning of adding two real valued functions. Alright, but then again you see clearly that these two give us compositions. This one is f composition h of x and this one is g composition h of x. And then once more you apply the definition of class, this time in the other direction, I mean opposite to this one. Here you had the sum of two functions, so you wrote its meaning. Here you have the meaning, now you have to write the sum. Or you can think of it this way also, you consider this and then you write what it means. Just like this one means you add the values of f and g at that input, this one also means the same thing, add the values of f composition h and g composition h at x, that means this. Okay, so that is how you have this. So what does this mean? It means that this function and this function both give us the same output for a given input x. So not only are they having the same domain and same codomain, but they also act identically. So that is why they are the same function. And next we go to the one involving multiplication. And this second identity also is proved in exactly the same manner. I mean, not of course identical, but the only difference is that there you had class, here you have multiplication, that is it. Here also one can see that f dot g composition h and f composition h dot g composition h both map the set of real numbers into itself. So for these two functions also the domain and codomain are both equal to R. And then we see whether they act similarly on the elements of R. So you take any element x in R and then you apply this one to x. Again same thing, this means because you have composition, so it means f dot g evaluated at h of x. But then here you have multiplication, so the values will be multiplied. Okay, so you have f of h of x dot times, actually I should say, g of h of x. But then again just as before, this one is f composition h and this one is g composition h. And then again by the definition of the product of two functions, this equals this, and that is why they are identical. Next, number 3, we are again given two functions, but this time two concrete functions, f and g. And for these functions we have to find both g composite f and f composition g. And you can understand of course that for both f and g the domain is the set of real numbers and so is the codomain. So both these compositions make sense. There is part 2 also, obviously, because you can see part 1 here, but that we will write afterwards. Let us first solve this one. So with the understanding that the domain and codomain are both the set of real numbers, you take any real number x and we apply say first g composition f on x. So that equals g of f of x. Now what is f of x? F of x is the ordinary absolute value function, modulus, and then you apply g on that. So now you have to replace x with that input, mod x. So this is what you get. This is the function. Note that here you cannot just suddenly write simply 5x minus 2, because what you write here depends on the sign of x. If x is a non-negative real number, then you can write x. Otherwise, if x is negative, you have to write minus x. So in that case, it will be mod minus 5x minus 2. So it's better to keep it like this. And then next we calculate f composition g, which is f of g of x. Now g of x is this, so we put that here, and f of that is its absolute value. Now something happens here which you were not able to do here. You did not really know whether x is positive or negative. X can be anything, right? However, now you look at what you have inside the outer modulus. Inside you have absolute value which cannot be negative, and that is why here you can lift the outer modulus and simply keep one modulus, just simply the absolute value of 5x minus 2. You cannot, however, go one step more and simply write 5x minus 2, which may be negative. So you can go this far, and if you notice, you have got g back. So f composition g is actually equal to g. And next we see part 2, where this time f of x is 8x cube and g of x is x to the power 1 divided by 3. That means the cube root of x. Note that here also the domain and codomain are both equal to the set of real numbers for both the functions. You have to be careful when there is a square root function, the square root function, which is the non-negative square root, because in order to get a real valued function, for the square root function you have to choose only non-negative real numbers as your input. If you take negative input, then you will get a non-real complex number as the output. But for cube root, that is not a problem. Every real number has a real cube root. So again we take any real number x, and first we calculate g composition f of x, which is g of f of x. Now f of x this time is 8x cube. So g of 8x cube, and g is the cube root function. So we get the cube root of 8x cube, which is just 2x. Cube root of x cube is x, and 8 is 2 cube, that's why you get 2. And next we consider f composite g. F composition g of x is f of g of x. This time the cube root comes first, and then you apply f on that. So that is just 8 times the cube of the input, and the input now is the cube root of x. So you get 8x. Next we have number 4, where a function f is given, which is 4x plus 3 divided by 6x minus 4, where x is not equal to 2 divided by 3. Although we do not need this, but let us take a few moments to see what type of function f is. Recall that f is a rational function. What is a rational function? It's the ratio of two polynomial functions, which in our case are 4x plus 3 and 6x minus 4, both linear polynomials. We need this extra condition x not equal to 2 divided by 3, because at this x value the denominator becomes 0, and division by 0 is not allowed. Actually division by 0 is allowed, but it is not allowed here because you want a real number as output. If you allow division by 0, you have to do some things, then you will get something else, and I am not talking about that vague notion of infinity. You can divide by 0 and really get something, but we do not have to worry about those things. So coming back to our main thing, we have to show that f composition f of x is equal to x for all x not equal to 2 divided by 3. In any function that looks like this, there is something in the background which usually is not mentioned, which you understand that x is a real number. The only thing that we have to make sure is that x is not equal to 2 divided by 3. So that is why whenever you read something like this, for all x not equal to 2 divided by 3, it means that for all real numbers x, none of which is equal to 2 divided by 3, you have to show that this is true. And then it also asks what the inverse of f is. Because the question is not really that difficult, at least the first part where just you have to calculate f composition f of x, there is a tendency of rushing through the calculation. But let's do it slowly. Let us first take any real number x, and this time we are really writing things explicitly. Let x be in R and x is not equal to 2 divided by 3. Alright. Then clearly f of x is this, it's given. Clearly this is a real number. Alright. But can you again apply f to this? Just like that? No. You have to make sure that this is not equal to 2 divided by 3, because that is the condition, right? If your input is not equal to 2 divided by 3, then only you can apply f on it. And now in this next step, if we once more apply f, this is our input. Who knows, maybe for some x this becomes equal to 2 divided by 3. If so, then that x has to be avoided. Let's see what happens if we suppose that this is equal to 2 divided by 3. Are we then going to find some possible value of x? Let us see. So next we suppose just that. Suppose that there exists an x, y here, we are coming to that, okay. Suppose there exists a real number x for which this thing is equal to 2 divided by 3. Because this expression loses meaning when x is equal to 2 divided by 3, that is why we are taking this type of x. Alright. But then, what do you have from this one? If you do a little simplification, a little algebra, 3 times 4x plus 3 is equal to 2 times 6x minus 4, or 12x plus 9 is equal to 12x minus 8, or after cancelling these 12x's from both sides, you get 9 equal to minus 8, which of course is not possible, and that is why this will never happen. That's what we have written. So no such x exists, i.e. f of x, which is this, is not equal to 2 divided by 3 for all such x, which means that yes, this is also not equal to 2 divided by 3, and that is why we can now apply f once more on this. So next we are going to write hence. So we have finally started our calculation of f composition f of x, which is of course f of x, which is this. And now we have to be careful. What is the function f? It's a ratio, right? 4 times the input plus 3 divided by 6 times the input minus 4. And now the input itself is 4x plus 3 divided by 6x minus 4. So you have this. You see it once more. 4 times this plus 3 divided by 6 times this minus 4. Alright. And next we have to be really very careful. 4 times 4x plus 3 plus 3 times 6x minus 4 divided by 6x minus 4. This is just the numerator. And a similar thing happens in the denominator also. 6 times 4x plus 3 minus 4 times 6x minus 4 divided by 6x minus 4. So in the next line we do the multiplications. 4 times 4 is 16, 16x plus 4 times 3 is 12 plus 3 times 6 is 18, so 18x plus 3 times minus 4 is minus 12. Okay. Then in the denominator 6 times 4 is 24, so 24x plus 6 times 3 is 18. Minus 4 times 6 is minus 24, so minus 24x minus 4 times minus 4 is plus 16. So you see that here 12 and minus 12 cancel each other, and in the denominator 24x and minus 24x cancel each other. And the numerator becomes 16x plus 18x, that is 34x, and the denominator very conveniently becomes 18 plus 16, that is also 34, same thing, no? And then after cancelling 34 you have x, and this is what you wanted to show, right? But now the next part asks us about the inverse of f, and the inverse is related to this fact because from this equation it follows at once that the inverse of f is f itself. Applying f once you get something, and applying f once more you get the original thing back. So that is why f itself is its own inverse. Next we have 5, which has 3 parts. We are looking at part 1 here. State with reason whether each of the following functions has an inverse, that is whether it is invertible. And the first function is f, which maps the set of these integers 1, 2, 3 and 4 into the singleton set consisting of the integer 10. And of course this is the only possible function because there is only one possible output, so that is the output, whether the input is 1 or 2 or 3 or 4. Now we have to say whether this is invertible, that is whether this has an inverse. We will see the other 2 parts afterwards. So let us first solve this one. This function f has no inverse, and the reason is that it is not a 1-1 function. It is not 1-to-1. You can just write any one of these things. I mean, here you just write that f of 1 and f of 2 are equal, both of them are equal to 10, although 1 and 2 are not equal. Different inputs are giving us the same output. So how can it be 1-to-1? It's 2-to-1, and actually 4-to-1, although we do not say such things. It's not 1-1, and being not 1-1, it's obviously not bijective. Bijective function is 1-1 and onto, and only bijective functions have inverses. So that's why f has no inverse. Next, number 2. Here the function has been named g, and this is the domain consisting of 5, 6, 7 and 8, and the codomain consists of 1, 2, 3 and 4. And the function g maps 5 onto 4, 6 onto 3, 7 onto 4 and 8 onto 2. So you can see that here also it is not a function that has an inverse. That is because it is not a bijection, and which comes from the fact that this one also is not 1-1. Both 5 and 7 get mapped onto 4. So it is not 1-1, so how can it have an inverse? And finally we have part 3, where the function is h, and this time the domain consists of 2, 3, 4 and 5, and the codomain consists of 7, 9, 11 and 13. Actually by now you have realized that these numbers do not really have any significance, and the rule defining h is this: h maps 2 onto 7, 3 onto 9, 4 onto 11 and 5 onto 13. So that order also has been maintained. This has an inverse because it is both 1-1 as well as onto. Why is that so? Well, first you look at the 1-1-ness of the function. distinct inputs are getting mapped onto distinct outputs. 2 to 7, 3 to 9, 4 to 11, 5 to 13. There is nothing like this. It's like this. That is why it's 1, 1. If you really want to write in the, of course you have to write in the solution why it is 1, 1, so you write like this. It is 1, 1 because distinct inputs have distinct outputs under the function h. And what about ontoness? Ontoness requires that every element in the codomain has a pre-image. That is also easy to see. 7 has the pre-image 2, 9 has the pre-image 3. So you go in the opposite direction. 11 has the pre-image 4. What does it mean that 11 has the pre-image 4? 11 is the image of the element 4. So 4 is a pre-image of 11 or inverse image, whatever you want to call it, under the function h. And 13 has 5 as an inverse image. That is why the function is onto as well. So being 1 to 1 and onto, it is bijective, and that is why it has an inverse. So you have to write all these things. Okay, I won't write it for you. But let me write what the inverse function itself is. So by the definition of an inverse function, the domain of the inverse should be the codomain of the original function. That means 7, 9, 11, 13, 9, 11. And the codomain should be the domain 2, 3, 4, 5. And the rule will be, it will do the exact opposite to what the rule for h is doing. H maps 2 onto 7, this one should map 7 onto 2. So just like that, in place of 3, 9, you have 9, 3. Here you have 4, 11, here you have 11, 4, and in place of this you have 13, 5.